Hi calculus students. These notes or this video is explaining the box problem from the optimization problem set. So we have a manufacturer wants to design an open box. That means it's not going to have a top with a square base and a surface area of 108 square inches. What dimensions will produce a box with the maximum volume? So the first step is to draw a picture of the box and label the dimensions with some variables. So the key understanding is like, what does it mean to have a square base? So it's this idea that like if we start with a square, and I'm going to kind of draw it sideways, but imagine that's a square in 3 dimensions. So that means like if that's x, that's also x, and then we kind of go up from there to get our box. Get something like that. So then we have 1 dimension. So also now that I drew it, know that this. Maybe I'll rewrite where this x is. That x is there, and maybe put my y over there. So we have an x by y box. It also might be helpful to draw what this looks like if we kind of like lay it flat so we can think about surface area. So we can kind of imagine like the square base with like 4 rectangles coming off of it. And then this is, all of these are x. And then the length of each of these rectangles is y. And that can help us think about a formula for surface area. So then if we want to, now next step is to use your variables to determine expressions for the volume and surface area of the box. So volume is probably a little bit easier to think about. I know volume is length times width times height, and in this case, 2 of those are the same, right? We have x by y. So we would say volume equals x squared times y. And from there, we can also, let's think about a surface area formula. So for surface area, there's 5 different rectangles, and I'm adding up the area of each. So there's 1 square. So the area of that 1 square is x times x, or x squared. And then there are 4 of the exact same rectangle, which have a length of x and a width or height of y. So then I would say plus 4xy, representing these 4 rectangles that each have an area of x times y. So that's my surface area formula, and then I also have a specific value for the surface area that's set. It's 108, so I might as well just say 108 equals x squared plus 4xy. Okay, so the next part is to determine a volume function as a function of 1 variable. So right now I have my volume as 2 variables. I'm trying to write it as 1. So the idea is let me isolate a variable in my surface area formula and then plug in for that variable into the volume. So to do that, if you look at should I solve for x versus y, because x is quadratic, that should give you a clue that it'll be easier to solve for y. So if I'm isolating y here, I would subtract x squared over. I'm going to show that here. So I get 108 minus x squared equals 4xy, and then I would divide by 4x, and I'd get y equals 108 minus x squared over 4x. And from there, I might want to think about like how that simplifies a little bit more. So I could break it up and say 108 over 4x and minus x squared over 4x. I'm kind of out of space. Maybe I'll do that over here. Okay, so that looks like 108 divided by 4 is 27. So this would become 27 over x minus, and then I have x squared over x, which one of those x's cancel, right? The x on the bottom cancels, so it becomes x over 4. And this is kind of a nice expression for y. So now, when I go to write my volume formula, I'm going to just substitute this expression in for that y, and it's going to give me my volume in terms of just x. So that looks like x squared times the quantity, 27 over x minus x over 4. And the last part of this is to say, what is your domain? So the key for that is to go back to the original problem, thinking about, is there any restrictions on what x can be? Well, if I have a box, it must be true that x has to be some positive number, right? So x has to be greater than 0, and that's my domain, right? It could be, other than that, it could be anything. I mean, at some point, it's not going to be possible because it's going to, like, if x is too big, there's no way I'm going to get my surface area of 108. But we don't have to think too much about that for now. We'll just kind of leave it at that. Okay, so now it's time to take a derivative. Before I take a derivative here, like I could do the product rule, but I'm going to see if distributing it in that x squared makes my life a little bit easier. So when I distribute in x squared, I get 27x squared over x minus x cubed over 4. And then there's an x that cancels between the top and bottom in my first term, so that becomes 27x minus x cubed over 4. And this looks like a lot easier to take the derivative now. So especially if I consider this kind of like 1/4 x cubed, then it's a lot easier. So then my v prime would be 27 minus 3/4 x squared. And from there, I would like to know what my critical point is, so I'm going to set it equal to 0. Subtract 27 over. And then I would multiply both sides by 4/3, or negative 4/3. So that's like dividing by 3, I get 9, and then multiplying by 4, I get positive 36. Equals x squared, square root both sides, and x equals plus or minus 6. Oh, you can't see my work, sorry. Or maybe you could, I'm not sure. All right, so from there, now I know, well, I don't want the negative 6, right? Because if I have negative 6, that doesn't make sense as a dimension. So I know like one of my dimension for x would be 6 inches. That's one of my dimensions. To get y, I could plug back into any number of places. I'm going to choose to plug, maybe I'll plug back in to this version over here. That seems like it might be the nicest thing to plug back in, but really you could do any version of plugging back in. So to find y, I would say y equals 108 minus 6 squared over 4 times 6. So this gives me 108 minus 36 over 24. And at that point, probably want to use a calculator. This ends up giving you a value of 3. Okay, so what's that telling you? Now we know that the dimensions that we get from this critical point are 6 by 6 by 3. How I know there's 2 6s? Because I know there's 2 dimensions of x in my box, and then there's 1 dimension of 3, and these are inches. And now the only thing I just want to confirm is, like I don't have a closed interval, so I'm not going to do my t-chart, but I do want to make sure this is, if I'm trying to maximize it, I want to confirm that 6 actually is a critical point to give me a maximum. So I'm just going to quickly like do my little first derivative test and think about when is the derivative positive versus negative. So if I plug in 0 to my derivative, I get something positive. If I plug in something larger than 6, I see that that's going to be something larger than 27. So I'm going to get something negative, and it is in fact a max at 6, so that confirms that this will give me my maximum volume. If I was interested to know what the maximum volume actually is, it doesn't ask me, but I could just do 6 times 6 times 3. That ends up being 108 inches cubed, which is interesting because that's the same thing as the surface area, but I believe that is just a coincidence. All right, so there's that problem explained. You're welcome. Bye.